Welcome you all. Myself is Karthikeyan, working as the faculty in the Department of Aerospace Engineering at B.S. Abdurrahman Crescent Institute of Science and Technology, Chennai. This video is a part of lowest by aerodynamic course. Here I am going to cover the topic downwash, induced drag, Vertex filament, Biot Savart law and Helmholtz theorem. I hope at the end of this video you can able to get the answer for the following question, because these are the questions normally we will have in our mind. I will read the questions one by one. So first one, so what is the difference between infinite wing and finite wing? The second one, what is the significant factor involved in three-dimensional analysis compared with two-dimensional analysis? Okay. Third one, how vertices are formed in the wing section. Then fourth one, what is downwash? Okay. Then what is induced drag? What is the meaning of the notations? So we are using different type of notations, so we will come to know what is the meaning of individual notations. Then relation between geometric angle of attack, effective angle of attack and induced angle of attack. And similarly the why induced drag calculated in the wing section, okay, why not in the airfoil. Similarly, why profile drag calculation in the wing section, calculation in the airfoil is almost equal to wing section, that also we will discuss. Then how to calculate the total drag of an airplane. Then where I can use the vertex filament concept, because it's questions normally we will have, so we don't know what condition we can able to use for the vertex filament concept. Then how to calculate the induced velocity for the arbitrary point. When I am doing analysis, I need to calculate the velocity of the arbitrary point. How we can able to calculate, that also we will discuss. Then definition and application of Biot Savart law as well as Helmholtz theorem. And finally the small topic like the meaning of geometrical twist, aerodynamic twist, wash in, wash out. So all these things we will discuss one by one. Just you read the question right now. 1 second, at the end of the video you come to this page, then you will get a clear idea about all these questions. So now we will hear the difference between infinite wing and finite wing. So normally infinite wing we can call it as like a airfoil, okay. Then finite wing normally we can call it as a general wing, because in the aircraft we have a finite wing section, so that is why it is called as a finite wing. Infinite wing means like suppose I am having the wind tunnel, I am placing the airfoil wing section model in the inside of the test section, okay. So the model may be occupy the full space of the test section, so we cannot get the clear idea about the aerodynamic characteristic on the tip of the wing. So we are analyzing only for the two-dimensional way. So that is why the airfoil is called as infinite wing section and normal wing is called as the finite wing section. So this is the main difference between airfoil and wing. And similarly the aerodynamic characteristics also is totally different from airfoil and wing section. Some of the point may be common, but generally it will be different. So in the airfoil will be a cross section of your wing section. Next we must be know how lift drags are produced in the airfoil or wing section or in the aircraft, okay. So when we have the flow over an airfoil, okay, normally we are considering the two major things. The first one will be the pressure, and the second one will be your shear stress, okay. So here you can see the pressure, so here you can see the pressure diagram, okay, and here you can see your here you can see the pressure diagram, and here you can see the shear stress diagram, okay. When you are comparing the pressure and the stress, so both are in the same unit, okay. The pressure also Newton per meter square and stress also Newton per meter square. So how we can able to differentiate pressure and stress is nothing but the pressure is nothing, the unit will be Newton per meter square is a force by area, amount of force acted on the area, okay. So when I want to consider the force, pressure means the force is acting perpendicular to the surface. Suppose it may be a surface, if the force is acting perpendicular to the surface, this is called pressure, okay. Suppose I am having the object like this, okay, if I am having the forces acting parallel to the surface, so this is called stress. So this is the main difference between pressure and stress. So when you have the aerofoil, flow over an aerofoil, we are also facing the these two things, also pressure and stress. So first you have to make it very clear when I will consider the pressure and when I will consider the stress, because these are things will be very helpful to understand the other concept. Suppose I want to know what is the amount of forces acting on my aircraft. Okay, so here you can see, so aerofoil will be facing off pressure and shear stress. Okay, there are two in the imbalance of pressure and shear stress will be creating the lift. For example, I am just making of magnitude of upper surfaces forces and lower surfaces forces. So the imbalance of upper surface forces and lower surface forces create the lift. So always the lower surfaces of pressure will be the higher. Okay, that is why we are feeling the lift. If the lower surfaces pressure is less, we cannot able to create the lift. Okay, so this will be working based on the Bernoulli's principle. Okay, based on the Bernoulli's principle only, we are facing that upper surfaces low pressure and lower surfaces will be high pressure. So now the component of resultant force. So we are knowing that there are two main things, that is pressure and shear stress. Okay, we want to mention the or we want to find out the magnitude of these forces. First we are taking the resultant force. So the resultant force of magnitude and the resultant force of magnitude will be placing on the direction like this. Okay, then I want to make it a component because it's an inclined force. So I want to make a component that is a vertical component and a horizontal component. So the vertical component will be vertical component will be lift force and the horizontal component will be the drag force. So here also we can see, so if I am having the imbalance of these two things, automatically moment will be created. Okay, so we are considering lift, drag and moment. Similarly, moment is based on your engineering mechanics approach. So force into perpendicular distance. So I can able to take a moment in the leading edge, or I can take a moment in the 1/4 of the card. So depends upon the location, I can able to use a notation. So moment and lift, drag, force values. Okay, so in this picture will be helpful to know about the importance of the aerofoil, because we are having so many object for maybe the bluff body or a streamlined body. Okay, this may be a bluff body, so these are the streamlined body. Okay, so the arrow mark indicates the amount of drag produced by the individual component. So that is why we always prefer the using of aerofoil for reducing the drag value in our aircraft. So now we will move on to the geometry of the wing section. Okay, because the difference between two-dimensional and three-dimensional based on your axis. So two-dimensional will be called, normally we will refer as aerofoil. Okay, when you come for the three-dimensional, that is for your wing section. Okay, so here I am giving some important terms we are using for the aerofoil or wing section regularly. So you can see here a chord line, this is a leading this is aerofoil. So the leading edge, the most first part of the aerofoil called as a leading edge. Then this one is trailing edge. The line joining between leading edge and the trailing edge is called as a chord line. Okay, then you can see the dotted line, that is a line exactly define the making the aerofoil with two equal parts. Okay, that's a mean line making a mean of the aerofoil, so it's called as a mean camper line. Okay, then the distance between the upper surfaces and the lower surface is called as thickness. So distance between the upper surfaces and the lower surface is called as thickness. Then the distance between the chord line and the camper line is called as camper. Okay, so just I repeat it, leading edge, trailing edge, line joining between leading edge and trailing edge called as chord line. Then dividing the aerofoil into two equal parts. Okay, that is a line is called as a mean camper line. The distance between the upper and the lower surface is called thickness. Then the distance between chord line and the camper line is called as camper. You come here, this is for wing section. So for the wing section, so this is for your front view, this is for your top view. Okay, so here is showing the rectangular wing section. This is for leading edge and this is for your trailing edge. Okay, then again the leading edge, trailing edge, the distance between the leading edge and trailing edge is called as a chord line. then the total length of the wing section called as span. So total length of the wing section is called as span, and the yellow color marked as the area. So you have to make it very clear. Another one important parameter is the aspect ratio. So aspect ratio is also important. Aspect ratio is nothing but s squared by a. S nothing but span, S nothing but span, okay, then area referred by the A, okay. So length A will be in the meter, okay, area will be in the meter square. So you should not get confused, okay, this is in the meter square, okay. So I want to find out the area, I want to find out the aspect ratio. So it is a ratio between x squared by A or B by S or S by C. S by C will be the aspect ratio for the particular wing section. Okay, suppose I am seeing the aircraft, I am seeing the wing section from the front view. Okay, if I am having a position of the wing section like this is called dihedral angle. So in the dihedral angle, suppose I am having a position like this instead of like this is my center line. If I am having a position like this is called anhedral angle. So this is anhedral angle, this is called dihedral angle, and this is called tip of the wing section, and this is called root of the wing section. So this center portion is called as tip of the wing section, and this one is called as root of the wing section. So these are all the terms you have to remember, because hereafter you are going to use frequently all these terms. So you are familiar of these things will be very, very essential. So next we on to the next slide. So here I am showing the some of the examples of various wing section. For example, straight wing, it may be look like this, and sweep back wing, and tapered wing, and variable geometry wing. So variable geometry wing means the beauty of this wing will be we can able to change the position of the wing section, and this one is called delta wing. So these are all the some different type of the wing section. Okay, normally we use it for the designing of the aircraft. Then here you can able to get one important output for this particular slide. So now we come to know the aspect ratio we can able to find out by using of the wing section. So wing section may be a span B and area S, okay. So if I am having the like this, okay, then suppose I am taking example of airfoil. Airfoil already we defined as is nothing but infinite wing section. So infinite wing section means there is no any a finite dimension. It's a infinite length. So we cannot able to find the span for the particular wing section, that is a particular airfoil. So that is why the infinite aspect ratio not applicable for your regular wing section. So that is why the main difference between the wing section and the airfoil, we cannot able to find the aspect ratio for your wing section. Okay, suppose I am having the airfoil. If I am having the airfoil, okay, aspect ratio I cannot able to find it. Okay, suppose I am having the wing section, I can able to find the aspect ratio. So this is the main difference between the two-dimensional flow and the three-dimensional flow, because airfoil will be the two-dimensional and wing section will be the three-dimensional. So that is why your analysis of airfoil and wing section are getting different. So now we will come to the flow analysis of a wing section. So we are come to know that airfoil only for the two-dimensional, wing section having a three-dimensional, and similarly difference between the lower surfaces and upper surfaces pressure value make the airfoil will be lift. Okay, and we will come to know that component of resultant force will be the drag value and lift value. So if it is happening like this, we are occurring another one more important parameter, that is called tip vertices. So how the tip vertices are formed? So vertices are nothing but it's a curved shape of air motion. Okay, because of the lower surfaces and upper surfaces. For example, see here, this is my the thick line is represent the streamline pattern for the upper surface, top surfaces airfoils, top surface wing section, and the dotted line represent the streamline pattern for the bottom surface wing section. Okay, so because of the nature of the flow, okay, when flow over a wing section, the flow will be tried to move from bending like this way, because of the top surface is having a less pressure, and similarly bottom surface having a high pressure, so the steam lines are try to bend like this way. So this is the phenomena normally happen in the aerofoil. So this makes the formation of the vertices. So when the formation of vertices occurred in the wing tip, this is called as wing tip vertices. So this is from the top view and this is from your front view. So this will be the one more this is an important phenomena occurred in aerofoil. Okay, suppose you can see this picture clearly. Okay, so this is happening for the aircraft exactly. So here also happening like this. So each and every portion of your trailing edges faces that problem. So this is called trailing vertices, because it's only happening where this is a leading edge, this is a leading edge, and this is my trailing edge. Okay, so this is called trailing vertices, is happening like this, and it's happening on the tip of the vertices called as a wing tip vertices. So this is a very important phenomena, because we are already having so many drag. Apart from this, we are experiencing the this wing tip that wing tip vertices makes another one more drag, that is called induced drag. So how the induced drags formed and calculated, so we will see the further slides one by one. See here, this is the formation of the wing tip vertices. Okay, so in the real aircraft we will facing like this. So what will do exactly, because the aircraft flying frequently, suppose the first aircraft a heavy aircraft, okay, the second aircraft will be light aircraft, the impact of vertices wing tip vertices still it is available in the airport or in the atmosphere. So that is why we are not continuously operating the aircraft. There are so many examples available, so many accents also available in the net, you can search it to avoid that particular problems, because when the light aircraft is following immediately after the heavy aircraft, the light aircraft may be lose his control. That is why our ultimate aim is to reduce the wing tip vertices. Okay, and how to reduce the wing tip vertices, that is also available. For example, you can see the aircraft, so it may be a fuselage, this may be a wing section. You can see at the end of the wing section there is a small projection will be available. Okay, so this will be reducing the wing tip vertices. So the name of the portion is called as winglet. This name of this portion is called as a winglet. So by using the winglet we can able to reduce the wing tip vertices. Okay, so that effect is okay. Because of the wing tip vertices we are facing another one more problem. So these wing tip vertices changes in the velocity around the aircraft, that is called downwash. So for example, this slide will be explaining about the difference between the geometric angle of attack, induced angle of attack, and the effective angle of attack because of the downwash effect. Okay, so because of the wing tip vertices, so that induces the velocity over the nearby surrounding areas. So for example, in these cases, this is my free stream line. So this is my free stream line. Okay, initially. Okay, so this line and these lines are parallel. So this line and these lines are parallel. Okay, so this is for my free stream line. Okay, for this particular cases. Okay, because of the wing tip vertices, downwash effect will be happen, then automatically my free stream velocity having the angle alpha y, this is called induced angle of attack. So because of the downwash effect, my free stream velocity having the deviation. So that is called as that angle is called as your induced angle of attack. Okay, then that particular location is called as a local relative wind. So because this is our original reference wind. Okay, because of the downwash it having some changes, this is called local relative wind. So that is very, very important. Okay, so now we will see one by one about different type of angle of attack. So generally we are using the angle of attack that refers for the geometric angle of attack. Okay, normally we use a symbol alpha. Okay, to refer the angle of attack. Okay, that is called geometric angle of attack. So geometric angle of attack is nothing but the ratio, the angle between the chord line and free stream velocity line. So this is my free stream velocity line. So this is my chord line. So this is called exactly your geometric angle of attack. Okay, and similarly induced angle of attack. So induced angle of attack is nothing but the angle the angle deviated because of your downwash effect. Okay, then I'm calculating the effective angle of attack. How can I able to calculate the effective angle of attack? Effective angle of attack nothing but the angle between the local relative wind. So local relative wind, how we are obtaining? Because of the downwash, the free stream velocity having some deviation, so that is called local relative wind. So the angle between the local relative wind for the corresponding chord line is called as the effective angle of attack. Okay, then automatically, so induced angle of attack is nothing but when you minusing with geometric angle of attack and the effective angle of attack, I will get the induced angle of attack. So this is very important because when you see the aircraft, you may see the when you see the aircraft, you may see the main wing. Okay, and here you have some your tail wing. Okay, so this main wing create the vertices. Okay, because of vertices downwash effect happen. Okay, then automatically this downwash effect exactly impact on your tail wing section, because this is maybe my real free stream velocity line. Because of downwash effect, my real velocity line making is go like this way. So automatically, so this will be more important factor to be considered for the designing an aircraft. So because of this reason, okay, now the lift component of the lift will be repositioned from your original free stream velocity line to your local velocity line. So this is my new lift component. Okay, so because of downwash effect, I am facing another one more component called as drag. Is induces the drag value. So this is called your induced drag. So induced drag mainly will be occurred in the wing section only. So induced drag, for suppose I want to calculate the induced drag, then you have to follow the wing section geometry, not for the airfoil section. So by using the wing section only, we can able to calculate the induced drag. So now we will discuss about the various types of the drag, because that is our we always aim to reduce the drag. Okay, when you are reducing the drag, automatically your lift value will be increased. Okay, drag will be classified mainly by two way. The first one will be induced drag and the second one will be parasite drag. Okay, so induced drag also called as a wing drag, because the wing only produce the induced drag. So induced drag because of the downwash effect. Okay, so automatically this drag is called as a wing drag, and other than the component of the wing, what are the drags are produced is called as your parasite drag or profile drag. Again, the profile drag will be classified further category like form drag, skin friction drag, wave drag, and interference drag. So wave drag will be calculated only in the high speed aircraft. Okay, so we will not consider about, because still we are dealing with only subsonic speed, so we will not consider the wave drag. Similarly, interference drag, because of the component arrangement, so we are almost reducing the interference drag. So mainly we are concentrating on the pressure drag, skin friction drag, and induced drag. So these are the types of the drag. So our ultimate aim is to reduce the drag one by one, so that only we will get the maximum amount of lift. So now there is an equation to find out the total drag. So total drag CD equal to CD plus CDI. So here CD represents the total drag of an airplane, then CD represents your profile drag. Okay, then CD represents induced drag. So induced drag plus profile drag. So profile drag is nothing but a combination of pressure drag and skin friction drag. So skin friction drag and pressure drag, because of your viscous effect. Okay, there is a proof available in the Anderson book. Okay, so what is the amount of profile drag? What is the amount of profile drag calculated from your aerofoil section is almost equal to your wing section. That is why we are using the symbol. So we have the confusion about the symbols related to various factors. For example, like we are using for L and L dash. Okay, and similarly for capital CL. Okay, and similarly for small CL. Okay, so these are things you may have confusion. Okay, so wherever you are using for the capital L, this represents total lift value of an wing section. Okay, this L dash L prime, we call it L prime. This L prime will be represents a lift per unit span. Lift per unit span. This L dash represents a lift per unit span. This L represents the total lift for the particular aerofoil wing section. Like this, you can able to including for drag value and as well as for your moment value. Okay, so moment also M dash means moment for unit span, then capital M will be total moment for the wing section. Okay, then capital CL and small cl. Capital CL represents your wing section lift coefficient of lift value for the total wing section, then coefficient of lift for your particular aerofoil section. Okay, so you see in these cases we are considering only for the drag value for the aerofoil, not a wing section. You must be understand your drag value for the aerofoil. So that is a profile drag. The profile drag including of your pressure drag and skin friction drag. Pressure drag and skin friction drag. So pressure drag and skin friction drag. So this will be calculated from your aerofoil, because the calculating aerofoil almost equal to the wing section. That is why we are taking for the capital D and small CD. Then another important parameter, induced drag. So for finding the induced drag, you need to follow the wing section. Okay, so automatically my total drag for the aerofoil will be profile drag plus induced drag. So profile drag plus induced drag will be the my total drag of an airplane. Okay, so we have another one more equation for finding the induced drag, CDI. Okay, that is nothing but CL squared divided by pi EAR. This also formula will be available. Okay, you can check the textbook. Okay, so here also you can able to come to know, for finding the induced drag I need to value of aspect ratio, but we come to know aerofoil will be the two-dimensional. Okay, that is called as the infinite wing section. So for the infinite wing section we cannot able to find the aspect ratio. Only the finite wing section we can able to find the your aspect ratio. So that is why the importance of induced drag and aspect ratio will be very useful to understand the total drag value of an airplane. Okay, so next we will move on to so in the previous slide we had come to know the total drag will be depends upon the induced drag and profile drag. So now still we are dealing only with the inviscid incompressible flow, but simply we cannot omit that inviscid incompressible flow because this is very basic. So I'm giving the small idea about the difficulties of the flow models, because still we are taking only for the lower level of difficulties. We are not taking any advanced level of the parameters involvement. Okay, so just you can have a look how that the flow pattern will be flow model will be added one by one. Okay, then similarly for your software level also. Okay, so when you're using the software also, there are so many free software will be available. Okay, here that the basic level, the 3D vertex lattices. So vertex lattices nothing but your next level of vertex panel method. Okay, so 2D panel method, 3D panel method we are having. So that will be the advanced level of your vertex panel method. Okay, so here also when you're talking about a subsonic speed, we are talking about the lower level of difficulties. There are so many complicated problems will be available. Okay, so you should not omit any topic. So that's a basic. So based on that only we are developing the models one by one. So now we move on to the next topic, like vertex filament. Okay, so before that vertex filament, you must have some idea about vertex flow. There are so many aerodynamic flows we are considering. For example, like your uniform flow. Okay, then source flow. The flows are coming out of from the individual portion. Okay, source flow, and the same sink flow. The source flow, the streamlines are coming out of the outside. Then sink flow, the streamlines are going inside. And similarly this is called your vertex flow. So vertex flow is nothing but a concentric circle having a velocity, then the value of magnitude of the velocity vary from the origin point. So this is the nature of the vertex flow, because when you are talking about flow over an aerofoil, I need the combination of uniform flow and vertex flow. Okay, so that is why we are taking for the vertex flow here. And this is called state vertex filament. This is called a vertex sheet. The total arrangement is called as vertex sheet. Suppose I want to make a, this is vertex filament. So this is my vertex point. Okay, I am drawing a one line perpendicular to the flow. Okay, I am drawing a one line perpendicular to the flow. Okay, this is called state vertex filament. This is a vertex flow. I am making a line like this. Okay, this is called a state vertex flow. Okay, state vertex filament. Okay, single state vertex filament. Suppose I am placing the vertex filament like this. This is called vertex sheet. Okay, so this vertex sheet will be placed on the aerofoil, either it is a camper line or a car line. Okay, we can able to place like this. Okay, so it's a theoretical method to find out the value of your aerodynamic characteristic of the aerofoil. So this knowledge you must have, because the next portion we are based on this only. So vertex flow and state vertex filament, this is infinite. Okay, this is dimension will be infinite, minus infinite to plus infinite. Okay, plus to minus, so infinite distance. Okay, then placing of vertex sheet like this, vertex element like this called as a vertex sheet. Okay, then we can able to replace with a camper line or card line. So this is regarding about your vertex flow, because your Biot Savart law or your Helmholtz theorem purely based on this only. Okay, so that is why the essential. So now you come to for next topic, like Biot Savart law. Okay, so in the previous picture we are talking about state vertex filament. So state vertex filament the previous, and now we are considering the curved vertex filament. Now we are considering the curved vertex filament. Okay, having a vertex, having the vertex. Okay, then this is called vertex filament. Okay, if I am having a circulation like this circulation induces the flow field nearby the surfaces. That is an important phenomenon you have to remember. This circulation induces the flow field nearby the surfaces of the filament. Okay, so because of that your velocity will be induced. For example, I am taking one arbitrary point P. I am taking one arbitrary point P here. Okay, so this curved vertex filament induces the velocity on the point P. Okay, that how we are going to calculate, because we are not taking the total length of the curve, we are taking a small directed, this is called a directed filament, that is called DI, directed filament DI, having the vector distance of R. Okay, so this directed filament induces the velocity at the point P with the value of dV. Okay, so the derivation, the detailed derivations, the reference book given in the Anderson. Okay, Anderson textbook. Okay, so just I am giving the only the final form of your equation. So our ultimate aim is, here we are concentrating curved vertex filament. Okay, then in the curved vertex filaments we are having the vertex flow. So this vertex flow create the circulatory motion. So this circulatory motion created the induced velocity. Okay, so in this induced velocity we are calculating on the particular point P. Okay, which is distance of radial distance of R. Okay, for if I am having a like this, so this is the equation we are getting. So here your the gamma, this is called your strength of your vertex flow, gamma. Okay, then 4 pi parameter, then dI will be induced value. Okay, the filament, curved filament value dI, and R is a distance. Okay, so this is the equation for your Biot Savart law. So this will be very important relation in incompressible inviscid flow. Based on this only Helmholtz theorem and Prandtl-Liftelin theorem will be developed. So that is why this understanding of this Biot Savart law is very important. So here the ultimate aim is we will come to know how to calculate the induced velocity for the particular point P. Okay, now we move on to the next slide. So the previously we calculated about the curved filament. Now we are talking about infinite vertex filament in the straight line. So here you can able to see this is a straight vertex filament, having a dimension of minus infinity to plus infinity. It's an infinity distance. Okay, then similarly I am taking a point P in the arbitrary distance. Okay, then from the particular directed filament, so what is my induced velocity developed by the filament on the point B, we can able to calculate. So in the previous cases there is no any limitation. Here it's like infinite distance, so we are considering the limit from minus infinity to plus infinity, then automatically by solving some mathematical consideration, finally we getting the velocity value, induced velocity value V for the particular case. So we have to remember, so this case, this velocity only for the infinite vertex filament. So infinite vertex filament, by using the infinite vertex filament, the velocity induced value V equal to gamma by 2 pi h. The same way we have another one, that is called your induced velocity at semi-infinite vertex filament. So semi-infinite vertex filament is nothing but here we have only the one infinite distance. So we are starting with a to infinity. In the previous case, both the sides are infinity distance, minus infinity to plus infinity. So in these cases one will be starting from A and another will be the infinity. That is why it's called as a semi-infinite vertex filament. So by using the concept of Biot Savart law, okay, for calculating the induced velocity by the semi-infinite vertex filament on point P, we can able to calculate, we can able to derive from value V equal to gamma by 4 pi P. The previously we are getting the value gamma by 2 pi h. Here we are getting the gamma by 4 pi h. So these are two different value for the two different cases. This is very important because it will be helpful for understanding of the further derivation. Okay, and Helmholtz theorem is nothing but he establishes the several basic principle of vertex behavior based on the previous semi-infinite and finite cases. Okay, so you have to remember the two important point. The first point, the strength of the vertex filament is constant along its length. Okay, the strength of the vertex, suppose I am having the vertex filament like this, the strength of the vertex filament is almost constant. Okay, because of the distance or because of the some other parameter, the strength will not be vary. We have to consider the strength of the vertex filament is constant along its length. It may be infinite length or maybe a finite length. Okay, the strength of the vertex filament is constant. That we have to consider the first point. Then second point, vertex filament cannot be end in the fluid. Okay, for example, it should be in the infinite distance. Okay, not like a ending. Okay, otherwise it should be in the closed path. It should be in the closed path. So these two things, okay, either it should be a infinite distance or it should be in the closed path. So simply we cannot leave it alonely. Okay, so these 2 points are very important because this is called a Helmholtz theorem. So this is the outcome of the Helmholtz theorem. Because of this only we are developing the Prandtl developed the concept. Okay, so next we are move on to that last topic, like the lift distribution. So lift distribution for the particular wing section, we can able to see the picture. So here the tip almost like is 0. Okay, this is the tip of the wing section, the root of the wing section. Okay, then automatically when the distance vary from tip to root, the lift value gradually increases. Okay, this is your circulation motion. Okay, the development of lift distribution detailedly explained in your Prandtl lift length theory. Okay, that we'll see later. Okay, so now we will just I want to tell about the distribution of the lift from tip to root section. Okay, because it is depends upon the so many factor, like it may be terms like wash in, wash out, geometry, aerodynamic twist and geometry twist. Okay, these are the terms normally using for designing of your wing section. Okay, so what is the meaning of wash in? So wash in nothing but suppose I am having that position of the wing section like this. Okay, this is my tip of the wing section, this is my root of the wing section. Okay, so suppose washing means, so the tip of the wing section having a more angle of attack compared to the root of the wing section, this is called your washing. So tip of the wing section having the higher angle of attack compared to the root of the wing section is called as washing. Wash out just opposite. So tip of the wing section having a lower, tip of the wing section having a lower, this is my tip okay, this is my tip, this is my root, okay, so this is my fuselage, okay, just simply I'm putting for a fuselage, okay, so this is the tip and this is the root, okay, so tip of the wing section lower, having a lower angle of attack compared to the root, then that is called washout. And similarly aerodynamic twist nothing but, so if I'm having the wing section, I may use so many different type of the wing section, okay, so many different type of the wing section, okay. So because why I'm using a different type of airfoil, so why I'm using so many different type of the airfoil, because I need different lift values, so different lift value at zero angle of attack, so I need a different lift value at zero angle of attack, okay. So for that purpose I am having the different aerofoil section for the wing section. So if I am having the different aerofoils to create the different lift value zero condition, so that is called as a aerodynamic twist. Geometric twist nothing but either the aircraft may be in the same aerofoil, the aircraft may be in the suppose my wing section having a same aerofoil, but the chord length are different, okay. So the type of aerofoil is called as a geometrical twist. May I have the same aerofoil or a different aerofoil, my chord length are different, so that is called your geometrical twist. So these are the terms frequently used in your designing purpose. So wash in, wash out, aerodynamic twist and geometric twist. So these are the things very essential for covering of this topic. So I hope I try to cover all this topic. So once this topic is over, so what may be the next portion? So next portion is like that the calculation of induced drag, then total drag calculation and lift distribution, okay. So these are the next level of topics. So how I can able to obtain all this topic, then you need to read about Prandtl classical lifting length theory, okay. So by using of Prandtl classical lifting length theory, you will come to know the answer for all these questions, because we may have so many advanced technology, but still we are following only for the basis of Prandtl classical lifting line theory. So soon I will be upload that video, so you can check with YouTube frequently, okay, or you can check with my channel, so you can, the video will be available, okay. So thank you for watching this video, okay. So I have taken for reference of Anderson book, Fundamental of Aerodynamics, similarly Introduction to Flight. Apart from that I have taken so many references like YouTube references, SlideShare references, Wikipedia references and IIT professor notes, okay. So based on that only I am using these pictures and other things, okay. Then similarly total derivation you can check with the textbook. So this video will be helpful for only the highlighting of the topic, okay. So once again, thank you for watching this video.